Welcome back viewers. In today's video, we are going to take a look at the board scheduler. So this is the web link for the board scheduler. This is the GitHub page of board scheduler. And these are the resources for the board scheduler. And you can also download the code here. You can clone it using the web URL, or you can download it as a zip, or you can use the GitHub command line to install the board scheduler on your system. What is BORE? BORE is Burst Oriented Response Enhancer CPU Scheduler. So it is enhanced version of CPS, that is the completely fair scheduler, and the EEVDF, that is the earliest eligible virtual deadline first Linux scheduler. So it is using best of the both worlds, developed with the aim of maintaining these schedulers high performance while delivering resilient responsiveness to user input under a versatile load scenario as possible. So BORE introduces a dimension of flexibility known as burstiness for each individual task, partially departing from the CFS inherent complete fairness principle. Burstiness refers to the score derived from the accumulated CPU time a task consumes after explicitly relinquishing it, either by entering sleep, IO waiting, or yielding. This score represents a broad range of temporal characteristics spanning from nanoseconds to hundreds of seconds, varying across different tasks. Leveraging this burstiness metric, BORE dynamically adjusts the scheduling properties such as waits and delays for each task. Consequently, in systems experiencing diverse type of loads, BORE prioritizes tasks requiring high responsiveness, therefore improving the overall system responsiveness and enhancing the user experience. So if you want to check out, there is a demo available here in this link that we will check at the last. We can go ahead. So this is the graphical chart showing you the burst time bit count versus the burst code. So you can take a look at it. The scheduler tracks each task burst time, which is amount of CPU time the task has consumed since it last yielded, slept, or waited for IO. When a task is active, the burst score is continuously calculated by counting the bit count of its normalized burst time and adjusting it using pre-configured offset and coefficient. The burst score functions similarly to niceness and takes the value between 0 to 39. If you remember, we had checked out the low latency configurations in Ubuntu. I think in Arch also we have done that. Multiple Linux distributions we have done this, and in some of the Linux distribution you have to set the nice parameter. So nice parameter generally set at -19. So Pop OS has the nice parameter. I think Open Mandriva also has nice parameter. Endeavor Arch also I think has a nice parameter. You can set that. So that is this nice parameter that is being talked here in BORE scheduler. For each decrease in value by 1, the task can consume approximately 1.25x longer time slice. This process acts as a radix conversion from binary logarithm to common logarithm, converting between two different magnitudes, nanoseconds to minutes time scale, to about 0.01 to 100x scale dimensionlessly. As a result, less greedy tasks are given more time slice and the wake-up preemption aggressiveness, while greedier tasks that yield their time slice less frequently are weighted less. The burst score of a newly spawned process is calculated in a unique way to prevent tasks like make from overwhelming interactive tasks by forking many CPU-hungry children. The final effect is that an equilibrium between the opposing greedy and weak tasks. Weak tasks are usually CPU-bound batch tasks, and the modest and strong tasks usually IO-bound interactive tasks, providing a more responsive user experience under the coexistence of various types of workloads. So this is the diagram showing the functioning of BORE scheduler. You can go through that. Now, what are tunables? So if you remember, we had done the low latency settings for the professional audio video work. So those settings are called tunable. So what they do is they tune the kernel, or they will tune the system config, so that the part of kernel or the system that can be uh, configured by the user is called tunable. So you can tune your system, your kernel, using this command sudo system control dash w kernel dot scheduler shed underscore more is equal to 1. If you remember, in OpenSUSE I had shown you how to configure, how to tune your kernel. So I had given one example there. If you remember, we had used this system control command to do the configuration change or the tunable change in the kernel. So that same thing you have to do it here also, and it is you can do it in all Linux distributions. So you can enable the bore mechanism using the system controls settings at 1, or you can do it 0 to disable the bore mechanism. Now schedule burst cache lifetime. So range is given. How many nanoseconds to hold as a cache on for calculated average burst time of each child task. Increasing this value results in less frequent recalculation of average burst time. In barter for more coarse grain, that is the low time resolution, on for burst time adjustments. So this is much more advanced. So to understand this, first we have to understand the simple scheduler. Schedule burst cache lifetime. So how many nanoseconds to hold as cache the on for calculated average burst time of each child task. Increasing this value results in less frequent recalculation of average burst time. In barter for more coarse grain, that is the low time resolution on for burst time adjustment. So the range is given. You can check this out. Now schedule burst for atavistic, range is 0 to 3, default is 2. So 0 disables the inheritance of the average child burst time from the ancestor processes. 1 to 3 enables the inheritance of the average child burst time from ancestor processes using a topological hub stub style hierarchy tree rather than the traditional parent to child style. When this feature is enabled, nodes with only one child process are ignored while finding and calculating the ancestor descendant processes for inheritance. Any number equal to or greater than 1 also represents the number of hub nodes with child process count of 2 or more. Then that update child burst cache will recursively dig down for each direct child while traversing the process tree to calculate the average of descendant processes max burst time. Enabling this feature will improve the system responsiveness of the performance in situation where massive process working such as kernel builds is going on. So to understand this, you will have to understand data structures. You will understand the tree. What is a node? What is a child node? What is a parent node? So if you go back and check out the data structures, then you will be able to understand what is given here. Schedule burst penalty offset. How many bits to reduce from time burst bit count while calculating burst score. Increasing this value prevents the task of shorter burst time from being too strong. Increasing this value also lengthens the effective burst time range. So you have to take a look at what I'm teaching you. I will share the link here. Then you will have to have the knowledge of the basics. If you have a knowledge of basics, then only will we understand. Even I am not able to understand 100%, because you see, I'm not a programmer. I am an infrastructure guy. I know how to take care of the infrastructure. I know how to configure the servers and all those things. I know how to configure the your systems, desktop systems, and all those things. I know some knowledge of networking, but I'm not a kernel engineer. So many things I understand, some things I don't understand. So whatever I have got, I will share with you. I can share you the tips. So the tip I shared you is you have to have the knowledge of data structures, then only you can understand this. Now schedule burst penalty scale. So how strongly tasks are discriminated according to the burst time ratio, scaled 1 to 1024 of its precursor value. Increasing this value makes the burst score rapidly grow as the burst time grows. This means that tasks that run longer without sleeping, yielding, and IO waiting rapidly lose their power against those that run shorter. So In short, the board scheduler will give more priority to tasks that run for very less time. So CPU time slice, very short CPU time slice, they will give a priority. And those tasks which try to take longer CPU cycles, those will get low priority. So what is does is, so the processes which take very short time slices, those will get priority, those will be executed first, and the last priority will be given to those processes which take up a long time to execute, which take up long time slice of the CPU. Those will be given a lower priority. Schedule bus smoothness range is 0 to 1, default is 1. Schedule bus smoothness short, so range is 0 to 1, default is 0. So a task actual bus score is a larger value of one of the latest calculated score or its historical score which inherits the past score. So this is done to smoothen the user experience under the bus spikes condition. So what happens is the system will keep a count of the historical scores of a particular task bus time, and also it will calculate a newer score for the newer time slices that a process is using, and it will keep a check on this. So this is done to smoothen the user experience under the bus spike situations. Every time bus score is updated when a task is dequeued or yielded, its historical score is also updated by the mixing bus time divided by 2 into burst smoothness into the previous burst time. By this mixing occurs only when a previous burst time increases. Burst smoothness is equal to 0 means no smoothing. Now schedule bus exclude k threads. So keeping this value at 1, the bore takes effect on the non-kernel task. 0, bore takes effect on the non-kernel and the kernel task both. So default is 1, that is bore scheduler takes effect on the non-kernel task. Schedule bus parity threshold. So run to parity schedule feature flag is beneficial for throughput for slightly less responsiveness in trade-off, but it rapidly loses its advantage as a task count in a run unique increases. Thus, instead of consistently taking either behavior, an adaptive method is favorable. So when the this threshold parity is set to 0, bore simply obeys the run to parity. When set to greater than 0, run to parity is adaptively disabled if there are more tasks than this value in a CFQ queue, run queue. Schedule deadline smooth boost marks. So range is U32, default is unique initial enqueue webhook. So when a task is been enqueued with one of these flag, deadline is hard. So this is it for the board scheduler that is being developed and used in Cashios. So I will stop the video here, and what we will do is later in future is we will go through what is a scheduler, basics of scheduler, different types of scheduler. So it all depends on your inquisitiveness, your curiosity. If you support us by liking, by sharing our videos, by subscribing to our channel and making us earn something, because it takes hell lot of time to do such videos, then we will be very much pleased to come up with more videos that will increase your knowledge about Linux. Please do the needful, subscribe to our channel, share our channel, like our channel, give comments on our videos. That will be very much helpful, and it will be a very good interaction between all of us. So see you then. Bye bye.